Josh, nice seeing you connected. Switch on more lights. Okay, thank you for staying in the class and not dropping me, and giving me the opportunity to come and entertain you. So, so good news and bad news. Good news, today's meeting is very simple and short. I don't know how to fit it in 50 minutes. We can do it in like much shorter. Bad news, there will be another homework due probably on Monday. It is not my intention to do this way. It's a little squeezed because I was disorganized at the beginning of semester to give you first homework, but now we need it in order to accompany the class material. So if you do second homework sooner or later, it will be disconnected and will not help our understanding. And if you are, there is a chapter in calculus or in differential equations that you may refresh. If you had it before, if no, I'll provide all details. So the chapter that we need to, oh, hello, Alison. Nice seeing you connected. I'm just trying to see if I'm in the camera. Fourier transforms. Did you hear about it before? Absolutely, yes. Great. Fourier transform. Yes. No. Something. Okay. Okay. So let's live easy life today, but just it's a seed of thought for the future. So we will need this technique, and it will not be challenging. We will just plug in known things just so that you do not get scared with this concept. What are we going to do today? There are some slides, but you've probably seen they're not the best example of calligraphy and they're not typed. So let's briefly chat and then I'll go over the slides. So by now you are already certified experts in basic foundations of quantum theory and physical chemistry, but it's maybe a little irritation or surprising for all of you that originally we were declaring that this course will help to interpret experiments, predict something, and by now it was just boring and dry math. It's a little against the expectations. The reason is that we, as people who want to compete at the Olympics, one needs to start from like morning exercise and getting training and pumping the muscles to take the actual things. So we are getting foundations and pumping mathematical muscles, and so to say, and we will go in ascending order in more and more complicated applications that approach the real world. But today we will start the very first and very simple application. So if you looked through the slides, or if you have just general intuition, can you guess or suggest what would be the first model to start with? Like what can you think of most simple in for physics, chemistry, theory of electrons. Like, do you think we need to start with some molecule or some piece of solid or some atom? Like, just give some examples. What would you, if you strategically plan this course, what would you place like for this lecture? And we can skip it from recording if you are hesitant. Just or just give some examples. Huh? A ball you can see. Okay, good. So ball with quantum properties. Let's ask everyone, because we have plenty of time. We will finish before. Anyway, Sybil, what would you like to start this lecture? Which application would you be interested to do? Okay. Okay, movement of a ball. Okay, I think everyone likes balls, maybe because we discussed connection to sport. Joe? You can unleash your imagination and give some crazy examples. Okay, something about coordinates. So one system of coordinates, 2 times about the ball. Madam? Yeah. Which molecule would you like to start this lecture from? Okay. So I see that this gentleman took statistical mechanics and PChem2. Yeah, ideal guess, because we need to start from something ideal. Nate?
Something with hydrogen.
Okay, yeah, it would be most natural idea if we just think chemically. Yes, it's very reasonable. And hydrogen is like a ball, and it has some coordinates. Okay, good. But I have reserved some answer that will surprise you. Well, would you suggest something? Okay, electron position in crystal lattice. Yeah, thank you very much. It's a very good idea. Now I will combine everything. So when we already agreed by science or by discussions that the most challenging part of this course is electron with wave features. And I agree with Nate that simplest practical example for the electron is hydrogen atom, where electron is revolving, and therefore everyone starts freshman chemistry with it. But the positive ion, which attracts electron, oxygen is even more complicated. There are more than 1 electrons. So it's a good idea, but we postpone it for the future. Coordinates, yes, of course we need to do coordinates. So Joe was correct. The ball, we can take electron, charged particle with some negligible size, which has coordinates. And the question is, does it experience interaction with something? Like if it is a hydrogen atom, it is attracted to atom, right? And the closest, it's not exact answer, but I'm very pleased. Thank you, Lola. So motion of an electron through the solid lattice. Solid lattice is so many ions that they can be considered as homogeneous background through which electron is moving. So it's almost like a vacuum. And I'm going to offer you to dry your and my brains on very unpractical problem. Electron in a vacuum. So it's since electron is most challenging, the ions are a little easier. Let's took most complicated thing, but prepare, how to say, sample where we focus on this essence and nothing else, just to see its natural properties. So we will look on the artificial universe where like there is a whole space, no ions, and only one poor electron. What would it do in this universe? And can we apply your strong knowledge in foundations and mathematical backgrounds of quantum theory to tell something new about this problem? So what would be your benefits if you stay on this path? Would it be just another boring exercise, or we can take some message with us after we finish it? So do you expect any benefit from this boring problem? What? No, okay. This means I don't care which benefit say. But can you imagine anything positive if you learn more about how electron moves or stays in vacuum? How can we apply it to chemistry? Okay, good. And yes, but by now we do not have material. We have only one electron. But we can use it as a reference point. Like if you put it in electron in vacuum and then electron in your like metal or solid substrate or in molecule, we can compare. Will be there some similar features or they will be drastically different? Remember once upon a time we were looking at electron gun for the kinescope for old-fashioned TV. So there is a vacuum and there is an electron moving through. So it makes a connection. It's not quite chemistry, it's more like physics. But when this electron hits the surface with molecules that start flashing light when electron gets there, it's more chemical. But we are going to look on the propagation of electron in the free space. Okay. So what would you expect from before the electron? Two of you mentioned the ball like material object in a free space. So remember, we do not, like if it is some mass, we do not have Earth, we do not have gravitational center, it's just free space. So what this ball or this electron would do if we think intuitively on classical things? Can it start moving on circles on itself? Right, it's not very unlikely, right? Can it speed up or accelerate or decelerate on its own? Okay, now you taught me first law of Newton. So without external force, an object moves with initial velocity, right? So if there were no initial momentum, initial velocity, it will just stay, hang on in the center of this universe. If we let it go initially, it will keep going with continuous velocity. Make sense? So it is what we initially expect. But we already started to discuss the concept of wave function, of probability distribution. That it's not there is no point coordinate. So it is a distributed object. There are probability to find it here and there, right? So do you think, so by now we agreed that the center will stay where it was, or will move with constant velocity. But what would happen to the shape of this distribution? And probably it is most challenging scientific question. Well, we cannot publish paper on it because many people were solving this problem in the past. But if you were not exposed, it will be a little discovery in this room. So suppose we created this electron in free space that stays in the vicinity of like x equals 0. We may or may not let it some velocity, and we look on the shape, how it is distributed. Do you think this shape may change? Yes, no, you don't care. One answer, it will not change. Other, so one is done, not sure, not care. One is sure that it will change. One doesn't care. Sibel? Okay. Okay, don't care. So by vote 2 against 1, it will change its shape. Congratulations, you did a discovery. We don't need math, we just need democratic procedure. Okay, now next question. By some reason, right now we are just thinking intuitively, will this change get sharper, more condensed? Will it just electron become thinner and thinner and skinnier and skinnier, or it will become fatter and fatter and fatter? So what do you expect? Who votes for skinny electron? 1. Who votes for fat electron? 3. Who is not sure or doesn't care? 3. Okay, so by vote 3 against 1, we accept the electron will become fatter with time. Congratulations, you did another discovery. Basically, we predicted our class material for next week, for like 3 lectures. Because we already accepted the correct answer or most democratic answer, but you saw that there were not everyone agreed. So there were some doubts in the community, whether it should change or whether it should contract or expand. And here we can use the mathematical tools that we introduced and prove if this is going to go, if it really goes to expand or not. So you already did correct answer just based on your scientific intuition as a group, as a collective brain. But now, if it would be something new for science, we would, and we want to publish a paper, the method how we got this answer probably would not be accepted by the editor. We need something a little more rigorous, right? So we are going to practice the math that we and principles that we introduced to prove 2 things: that the electron will move center of the distribution will move with constant momentum, and second, that the shape of this distribution, whatever it was originally, will expand. How to rationalize it? I have a very wrong answer, so do not listen to me right now or listen critically. If it would be not one electron, if it will be just collection of classical electrodynamics charges in area of space, they would repel each other and they would try to get further away from each other. This is a very wrong way to think about quantum theory. The reason why it expands is very different. So do not even think about it. And if someone tells in front of you, tell you're wrong. You're the main outcome that we will learn in about a week from now, and after you complete your homework, I suggest we do it. We try to do it by Monday, if possible. If not possible, we can do it by next Wednesday, but no later. So by our effort in class and your effort at home, we will see. I don't have words how to explain it. It's all mathematical concepts, and let me try. But right now it may look like birds chirping to all of us. But after we do through this exercise, you will support it warmly. So by the concept of eigenstates, right, the electron can be composed of several eigenstates. It can sit with some probability in one, another. And in free space, the eigenstates are plane waves that move forward and backwards with different velocities. And if we give this and that percentage to the eigenstates that move with different velocities, and then we construct it back, we will see that our localized shape will have components that move with different velocities, forwards and backwards. And even if we have our favorite, preferred state which has the majority, it will describe the center, but other shoulders will move quicker or slower. And then in average, it will give this increase of the width. Make sense? I wouldn't be offended if you tell it completely makes no sense. But if you support, I'm grateful. Whew. Basically, we are done. Now I'm going to show slides, but do not expect much from me, and especially from my slides. They are very ugly handwriting. So focus on instructor. Maybe not the instructor, but the screen. Oh, different. So I'm going to jump and dance around the screen and point on some things there. So let's focus on it. Okay, and let's share screen. Okay, so we are starting new chapter. In previous years, presentation on MATLAB was at the end. We can do it a little earlier because you basically all done. You know how to use it, and then we can go forward with applying it to problems. So here is the homework one, which is really brief. Probably some of you already completed. Here, can you tell what it is? Can you give an just tell anyone? Adam is nodding, means you know what it is. Can you verbalize?
The note.
Yeah. Yeah. So it's German money before 2000. So whose faces are shown on American money? Presents. Guess who was on this German money? Right. So do you know the name of this mathematician? When we all take freshman classes with like 200 people in one class, there is a mathematical statistical processing of the grades, right? And there is a grading and distribution. Like you do not need to. Oh, okay, a joke. Hunters wake up bear in the middle of the winter and run out from it. And then journalist asking the survivor, "Oh, you are running quicker than bear." And, "No, I'm just running quicker than the other hunter." So yeah, it's black humor. So when we are in the freshman classes, you do not need to perform 100%. You just need to be on the top of others in the distribution. And which shape of distribution typically is a grade stake? Bell, yeah, bell shape. Or is there a mathematical name for this bell curve? Probability distribution, but is it named after any person? Yes. So it's this gentleman designed, you see this bell distribution here. So he designed this distribution, and we will praise him by using this distribution for describing electrons. We will assume that our electron is localized in space using this bell distribution. So homework. I recommend finishing it by coming Monday, and it will be like a little bit different date. And if everyone tells it is very, very hard, we can postpone it by Wednesday, but Monday is much more preferred. Maybe let's do it double credit to those who bring on Monday and regular credit on Wednesday. And then it's your choice. So the concept of Fourier transform that is hidden in this exercise is a key thing to practical description of this electron in a free space. And first, there will be exercise to do Fourier transform for the periodic function with these like steps. And then later, it will be practicing Fourier transform for Gaussian function. I'll speak maybe a little bit more about it on Friday, and you have time just to prepare yourself for it. Okay, last time we got approval of everyone. I don't remember by votes or by silence that there is a third way to predict future. If you know wave function of the past at time 0, we can get wave function at future time t by getting expansion coefficients and then plug it into the summation with 3 components: time development with energy of eigenstate, eigenstate itself, and expansion coefficient. We are going to practice this recipe in the coming week. We are going to look what are eigen functions for electron in a free space. We are looking going to look what are the energies of electron in a free space. Basically, it will be momentum squared over mass, only kinetic energy, right? And then we are going to use these expansion coefficients, which need to match bell shape of the original wave function. And then as a result, here, we will see that it will be bell shape that expands. So I'm playing open cards. There are no secrets. Yes, same thing. Okay. I'm hitting. Oh yeah, it is in the center. The Gaussian shape, and you can see even the equation. So this bell shape has deviation of the argument from central position, right? Squared. And then this squared thing is in the power of exponential. So the square thing is always positive. When difference is 0, e to the power 0 will be how much? 1. And if it is negative, like this number is positive, we put minus, and e to the power minus 10, will it be bigger than 1 or smaller than 1? Small. So everywhere away from center, it will go down, right? And one can speak about width by tweaking the parameter in the denominator. So this is what you taught me about first, Newton's law. So if an object doesn't experience any forces, then its position will be equal to initial position plus velocity times increment of time, right? So homogeneously move forward on a straight line. And it is our first hypothesis that we want to prove. I think here is a plan that I would try to follow. And I'm getting bored just looking on it. And probably you are getting 10 times more bored. So basically, we already know the answer and we know our tools. And now we want to play Age of Empires. No. We want to play the principle of ancient Romans, divide and conquer. We will take the whole procedure that we want to do, slice it on little steps, and then conquer each of them. So we're going to refresh plane wave concept. Then we will speak about momentum operator, which we already did in the past. Then we will chat if time-independent Schrödinger equation is applicable there. And it's one of the most, the problem is very simple, but it is one of the most strange applications of time-independent Schrödinger equation, because if you solve it for like molecules or for atoms, you have discrete states, right? There are only certain energies with certain quantum numbers which are allowed. Here, I'm just impatient. I cannot wait. Here, any energy will be eigenenergy. So any positive energy will be allowed. So it will be no, it is a quantum problem without quantization. So if you want smart words for it, it will be continuous spectrum of states. Okay, so eigenvalues of energy, eigenfunctions of Hamiltonian, which will be plane waves. And then third way to predict future that we just looked. So we need to plug in all bells and whistles to give the right answer. And then our expansion coefficient, the C sub k, should match the bell shape of the Gauss. And then we will combine everything and analyze the answer. Whew, I would fall asleep if I would be on the other side of the barrier. Equations are boring, but text is even more boring. Okay. I understand what I drew here, but I do not understand why. So I think I'm trying to introduce the plane wave, and it is what we were discussing our first several lectures. So the one of the possible wave functions can be considered as exponential with imaginary power, and something of the dimension of the action in the power of exponential. So momentum times position and divide by h bar constant to have overall dimensionality dimensionless, right? And exponential is just summation of cosine and I sine. If we remove time dependence, then this function will be spirals that we already drew in the lab. And depending on the value of momentum, they will be more or less vivid. So the higher the momentum, the denser the fringes, right? Okay. Here is a summary of two hypotheses, two open questions that I think we were much more successful in chatting it by words rather than looking on this ugly slide. So there are two hypotheses that if you prepare distribution in space, the center will move continuously and the shape will expand. So if you want to sound smart, we formulate hypotheses and then apply mathematical tools to prove them. But you already proved that these two hypotheses are correct just by simple voting. So mathematically, we can extract position center of this Bell distribution from the solution and follow whether it will go on a linear expansion. And then we can extract the width parameter. So I anticipate very much that by practicing this math, we will get Bell shape at the output as well, especially if time increment is equal to 0, then we should get input is equal to output. And then for the Bell shape that comes as the output, we should speak about width, right? The parameter in the denominator of power of exponential. And we should look on it as function of time and check whether it is constant or it grows or it becomes smaller. So by votes, we agreed that it should grow. So a little refresher on the momentum operator. So it is absolutely nothing new. It is what we already did before. So when we introduced the concept of the eigenfunctions and eigenenergies of an operator, we did a reverse engineering, right? We considered example of eigenstates of momentum operator as an example, and here is just a little refresher. So if we design operator of momentum as a minus imaginary unit Planck constant and derivative over space, and I suggest we look only on one dimension because 3 dimensions are too heavy for us, at least right now. And we consider the function that will be this plane wave times normalization constant. Then by applying this operator to this function, we will get this function back multiplied by the value of momentum. And it's not a big surprise that if one takes derivative over space of this exponential and one takes care of all constants, one will get this p up front. So does anyone doubt that plane wave is an eigenstate of momentum operator? Well, no, let's formulate. Who agrees that plane wave is an eigenstate of momentum operator? Yes, agree, disagree, not enough information. Not enough information, not enough information. 1 agrees, 2 agrees. Okay, no one disagrees, but no, additional things, additional comments are needed. So the only thing I can do at this point is to open a white page and try to write this calligraphy once over again, if you want me to, or we can follow once again. So the statement is that plane wave, which is here, right, is an eigenstate of this operator, right? Which means if we apply this operator to this function, we should obtain this function again. Maybe there are ways to highlight. No, only writing. So probably I will do better just pointing by fingers. So when we apply the momentum operator, so this one is P, right? We apply it to this circular box, which is phi sub P, right? And here in the next line, I'm showing the constant stays unchanged, normalization constant stays unchanged, and then we are applying the derivative to this function. So by taking the derivative, one is getting P at the front. Okay, maybe I should do it over again because I see some confusion in the eyes. So P phi equals minus I h bar ddx e minus I p x h bar minus I h bar 1 square root of n d dx e minus I p x h bar. So derivative of this stuff will be E minus I P X H bar. And then up front, we are getting everything except X minus I P over H bar. And we have a heritage from the previous step, I H bar 1 square root of N. Now we can practice cancellation. So H bar here and H bar there will cancel. And then we have I times I equals -1. And then we have minus, minus, minus. So it will be minus P divided by square root of N E minus I P X over H bar. And then we can identify it as minus pi times E I minus I over H bar P X divided by square root of N. And this last bracket can be identified as phi sub P. Make sense? Is it better agreement that we reproduce the function itself? So, okay. And probably if I would select plus sign here, it will be plus P. So it will be, one can take care of it. So here is the answer that I wish we obtain in about a week from now. So we are going to speak not about wave function itself, but probability distribution, wave function squared, absolute value squared. And we will select such initial conditions that wave function square will be bell shape. And our answer for time bigger than 0, absolute wave function squared, will be, I skip normalization factor, will be exponential, where in the power we have x minus x naught and minus momentum over mass times t. So the center of the wave packet moves forward. In the denominator, we'll have original width plus some factor times time squared. So it will become fatter and fatter with increasing pace. So all exhausting mathematical efforts will be directed towards getting this this result in following the protocols that we established. So this is very close to last slide, or maybe almost the last slide. So in order to obtain the result on previous slide, we need to make summation of the eigenfunctions, which will be plane waves. And each plane wave in this summation will have slightly different momentum. So it will be denser or sparser fringes. Make sense? Now we need to exponential with time dependence, where energy here will correspond to total energy for given eigenstate. And if for plane wave momentum is known, potential energy is not applicable because nothing is attracting or repelling. So the total energy will consist of kinetic energy only. So this eigen energy will be just momentum squared over 2m, right? So plane wave, momentum square over 2m. And then we need to find expansion coefficients to match initial conditions. So we need to find such C sub k to say in which percentage, in which proportion these terms will enter into summation to reproduce the bell shape at initial time. Make sense? Please support or tell if I need to speak more. Everyone Okay, yeah, thank you. Thank you for the support. And to find the C sub k, we will just practice this convolution of the bell shape at initial time and all plane waves with different density of fringes. And the practical mathematical expression of the thing is related to Fourier transform. Right now, we do not have time and I do not have wish to do anything else. I think it just sets a plan for our next 2 lectures. Yeah, here is an outcome of the Friday lecture. So we are going to expand this thing towards about this expression, but it's too early. It's just heads up. So lecture 9 is finished. And I remember some of you were asking about my research way ago. I just occasionally, last year, I was preparing my tenure talk and was preparing a couple of slides of examples, like how many different systems can be computed and described. So it's examples of what one can do with computational chemistry, not physical chemistry. It's just different subject, just on the account of entertaining, if anyone wants. So porous materials, metal organic frameworks, like metal organic complexes, which are independent interface of molecules and solids, nanowires, quantum dots of different shape, where one can have a solid in the middle and organic shell around. And then some examples when upon photoexcitation molecules break on pieces. I think it is enough for, yeah, this is an example of true collaboration. When collaborators do not compete, but support each other. And the principle of research, like synthesis and characterization. Okay, well, thank you for staying here. Looking forward to see you this evening in the lab, where we will get some very basics of programming with MATLAB. Yeah. Everyone is welcome to disconnect and depart. I'll stay here to answer questions if any.